So, we were talking about solving problems in the general area of heat transfer. I have outlined the other day the principle of solving some steady state problems, and today I intend to show you that beyond the conduction theories, how we can also apply some simplified principles in order to estimate some useful numbers for some practical problems. To start with, I would like to first discuss a problem based on the principle that it's there is a system from which temperature heat is being lost to the surrounding, and as a result of which the temperature is going down, and we can have a generalized expression for enthalpy conservation, which can be stated like this. So, net rate of enthalpy change is equal to rate of enthalpy in So, this is the generalized principle based on which we will solve some problem. Now, enthalpy is the heat content. So, mass specific heat, that is what, and the moment we say it is rate, so it is mass flow rate Cp into T. So, let us say or assume that we have a steel ladle which contains molten metal. So, ladle we know that is typically covered. There are slags also on top of molten metal, but because the ladles are refractory lined, and so therefore, from the surfaces actually heat is lost. All these surfaces, the ladles are basically cylindrical shaped vessels, and these are refractory lined vessel. So, basically that is the rate at which heat is being lost, kilowatt per meter square, and then we have significantly lesser amount of heat is being lost from the top surface, because there is a slag cover and there is a physical cover. So, it is about 10 kilowatt per meter square. This is the problem on which we want to apply the principle and find out that during the holding period or during the time the ladle is transferred from one place to another, what is the rate of temperature drop from the melt. Now, so let us say we have a 300 ton vessel. Let us say typically ladles have an aspect ratio of L by D is equal to 1, and it contains steel. So, steel has a specific heat value something around say 680 joules per kg, and we require that if we, and the density of steel is raw steel is 7200 kg per meter cube. So, these data are given to us, and we have to calculate the rate of temperature drop in the system, and we will assume that we can ignore the presence of the refractory layer here. So, whatever this heat flux values are given, we can assume that no heat is being absorbed by the refractory, and that these values are applicable right at the metal surface itself. For us, the existence of the refractory does not matter. So, there is an approximation we are doing here. Okay. Now, if we apply the principle here, net rate of enthalpy change is equal to rate of enthalpy in minus rate of enthalpy out, we will see into this system there is no heat input to the system. So, this is 0. Similarly, there is no heat output to the system. So, this is equal to 0. So, the net rate of enthalpy change is equal to the rate of enthalpy loss, and this can be mathematically stated, okay, as m dot m Cp is equal to minus q dot the corresponding area. So, there are several surfaces. One is the cylindrical surface, the planar bottom surface and the planar top surface. Okay. Let us see that a cylinder is what? A cylinder surface is equal to 2 pi r L. Similarly, a planar is equal to pi r square L. Now, in the problem, since we are given, so r and L values are not given to us, these are implicitly hidden in this. So, therefore, we can say that because it is a cylindrical vessel, the volume of the cylindrical vessel pi r square L is equal to 300 into 10 to the power 3 kg, where everything is in SI unit. Okay, or we can say that rho s pi d square L is equal to 1200 into 10 raised to the power 3. R is equal to d by 2, and then aspect ratio is given to be is equal to 1. So, therefore, we can say rho s pi d cube is equal to 1200 into 10 to the power 3. So, rho s is 7200, pi is 3.14. We can find out the cube root of d from this particular expression, and therefore, it comes out that L is equal to d is equal to 3.75 meter. Now, we are in business. So, we can apply this equation. So, the right hand side of the equation therefore becomes, so we have m is 300,000, Cp value we have taken to be 680, and then we have the rate of temperature drop, that is the term we have to calculate, and the first term here is, so we will bring that term here negative sign on this side. So, that is better temperature. So, we can say that this is 100 multiplied by 2 pi R L plus 100 multiplied by pi r square plus 10 multiplied by pi r square. So, summation of all the heat losses, that is what it is. So, this side also, if you see that this is going to be mass is kg, joules per kg per degree centigrade, that is the specific heat. Okay. And then we have degree centigrade by time, which is second. So, therefore, we have joules per second. So, this side is equal to what, and here also it is heat flux multiplied by area. So, that is dimensionally consistent. So, we can now solve this equation, and then we find out that minus the right hand side will come out to be, so 2 pi r L, this value you can easily calculate, because I have found out that by equating the mass with the volume times density. So, the 2 pi r L comes out to be something like 44.15 meter square. Similarly, pi r square comes out to be 11.04 meters square. So, if you substitute all these values, then you will able to find out that in terms of SI unit. So, this is going to come out to be 0.02 degree centigrade per second, or is equal to 1.2 degrees. So, this tells us, the negative sign tells us that the temperature is dropping at the rate of 1.2 degrees per minute from the ladle. So, by writing in an appropriate statement of energy conservation, we can find out that at what rate the temperature. So, if you know that from one place to another place it takes about 10 minutes. So, we can say that in that 10 minutes of transportation time, temperature is of the melt in the ladle is going to be dropping by 12 degrees centigrade, or if the initial temperature is 1600 degrees centigrade, then the final temperature at the end of transit is going to be 1588 degrees centigrade, and so on and so forth. Having discussed this simple energy balance description, we can now use a lump parameter model. Much more complicated problems can be solved through numerical methods, but as far as analytical treatments, these are basically the first hand estimates. This tells us that what kind of a value. It is not 100 degrees centigrade, it is not 1000 degrees centigrade, but it is of the order of 10 degrees centigrade, or for 10 minutes of transport. That is the kind of loss we will be expecting. So, first hand estimates can be usefully obtained by performing such simplified calculations. Now, the application of a lump parameter model basically is used when we see that there is, or we assume that there is a negligible temperature gradient in the system. Typically, suppose if you take a sphere, the temperature is going to be a function of the radial distance and time, because sphere exhibits theta and phi symmetry. So, it is only a function of the radial coordinate and time. But in lump parameter model, what happens is that t is taken to be a function of time only. There is no temperature variation within the sphere, and the sphere itself is characterized by a single temperature, single characteristic temperature, which is prevalent from the surface to the center. So, lump parameter models are applicable in many cases, particularly for those operations where we can have the thermal conductivity of the solid is quite large, because thermal conductivity of the solid, if it is very large, then what happens? Heat is going to go quickly, or heat is going to flow out very quickly, and as a result of which the gradient will become flatter, and therefore, we can say that lump parameter models are going to be applicable when the thermal conductivity is very high. And in terms of a dimensionless number, we know that from theory that bio number has to be small. And what is bio number? The bio number is h for a sphere ds by ks. That is what is the bio number, heat transfer coefficient multiplied by diameter of the sphere divided by the thermal conductivity of the solid, and this number of the order of, if it is 0.1 or so, of the order of 0.1 is maybe 0.4, 0.5. So, it is reasonable for us to apply. So, I will now demonstrate that how we can apply a lump parameter model in order to find out, say, a melting of an aluminum sphere in steel bath. So, let me pose the problem to you with these words. More details of these would be found in textbooks, etc. So, I am not going to discuss those. So, we have an aluminum sphere, and the aluminum sphere is, this is aluminum, and then we have the diameter of the aluminum sphere is 5 centimeter. So, this is d sub s, diameter of the sphere, solid sphere is 5 centimeter or is equal to 0.05 meter. This is submerged in a steel bath. We know that aluminum melts at T melting aluminum is approximately about 660 degrees centigrade. Let us say the steel bath T steel is about 1600 degrees centigrade. Basically the operation takes place that when you add aluminum shots into steel bath during deoxidation of molten steel. Okay. So, we are assuming only a spherical geometry because that gives us a lot of simplicity, allows a lot of simplicity to be simplifications to be made. So, the geometry is known, the volume can be calculated, radius surface area can be calculated and so on and so forth. So, once the liquid is there at 1600 degrees centigrade, you project an aluminum sphere and that aluminum sphere melts. Now, the fluid may be moving or the fluid may be stationary, and we must understand that the melting takes place because of heat flowing from the bulk to the interface. Now, if you do this parameter, suppose if you take H ds by Ks, in this case the Bio number, heat transfer coefficient, diameter of the sphere divided by Ks, and that Bio number is going to come out to be something like say 1600 is the value of the heat transfer, I will tell you, multiplied by 0.05, that is the diameter, and aluminum has liquid aluminum has a thermal conductivity, solid aluminum has a thermal conductivity in SI unit as 200. Steel has a thermal conductivity of 40, so 5 times more conductive material. Now, let us assume that the bath is stagnant. If the bath is stagnant, in that case we know that Nusselt's number diameter is equal to 2. If you say that sir bath is not stagnant, in that case we will apply the Range-Marshall correlation. Nusselt's number is equal to 2 is equal to 0.6, Reynolds number raised to the power half and Prandtl's number raised to the power 1 by 3. Prandtl number for aluminum is steel is known to us, so which is approximately about 0.1 or so. Reynolds, to calculate the Reynolds number, in that case what happens is the velocity must be supplied. We will specify you that velocity is equal to say 1 meter per second past the sphere. So, given the velocity, this term can be easily calculated because Prandtl number of the fluid is known, Reynolds number diameter based Reynolds number can be calculated given the velocity. So, Nusselt's number can be calculated. So, whether it is a moving fluid problem or whether it is a stationary, there is conceptually no difference as far as the problem that I am discussing is concerned. So, with the given velocity we can calculate the Nusselt's number, or alternatively if there is no velocity we can specify that the Nusselt's number is equal to 2. Through either of the two routes we should be easily able to calculate the corresponding heat transfer coefficient, and which is going to be is equal to 2 times Nusselt's number is equal to, so this is K fluid, okay, and then this is equal to P sub S. So, fluid thermal conductivity is roughly about, so you can say that this is going to be 2 multiplied by K fluid, which is 40 roughly, okay, and diameter of the sphere which is 0.05, and that gives you something like 2 into 4000 by 5. So, 8000 by 5 which is equal to 1600, and that is the value that I have substituted in this equation. So, if you do this now, so then you find out that this is roughly about 0.4. So, it is of the order of the small Bio number criteria. So, we can consider that there is no temperature gradient at the within the solid. Under that condition, what happens is whatever heat is transported into the solid from the liquid, because there is a temperature gradient, okay, it is 1600 degrees centigrade here, and the surface is melting temperature. Okay. So, whatever heat is transported here, that heat is consumed, or is equivalent to the latent heat requirement for the melting process. So, if you know this concept, then we can write down the equation, okay, and the equation is going to be now rho s times delta H latent into dr over dt. This is the heat consumed, due to heat requirement for melting in terms of latent heat, and then this is going to be equal to the H heat transfer coefficient multiplied by T bath minus T melt. That is the expression. So, supply and consumption, okay? And therefore, we can from this we can say that dr over dt, actual equation would be at the interface the equation would be R is equal to R sub. This is the interfacial energy balance equation actually in the full form, but the moment we apply the lump parameter model, this term becomes is equal to 0. So, this essentially tells us whatever heat is going inside the solid transported because of conduction, whatever heat is consumed because of the latent heat, that is exactly equal to the heat which is being advected by the fluid right to the interface. So, this is the energy balance equation. So, in heat transfer problems, in many cases you may not be able to straightforwardly use the governing equation which you have derived, for example, the Laplace equation, etc., and you may have to formulate the governing equations by considering that how energy is coming in, how energy is being lost, what portion of energy is being advected out of the system, and so on and so forth, and then you have to represent each term mathematically in order to arrive at the characteristics equation as I have done. That may be very, very important for us. Okay. So, ability to formulate those statements and then convert the statements into corresponding mathematical expressions will depend largely how clear your fundamentals are. Okay. So, therefore, I can say that radius is decreasing, and then a very simplified L delta T divided by rho s into delta H, and then you substitute the value. H is equal to 1600, then temperature difference is 1600 minus 660. So, that is equal to 940, that is the temperature difference. Then we have rho solid, aluminum density I think is 3200 or something, no, it is 2700 kg per meter cube, and then the latent heat is equal to 321,000. So, therefore, this value can be calculated, and then we can say that minus dr is equal to integral this from where? From r is equal to Ri to r is equal to 0. R is equal to final R is 0, complete melting time, that is what we want to, and this is T initial and T final. So, where this is initial, so final minus initial will give us the total duration of the time, T melting time, and that is going to be equal to 1600 multiplied by 940 divided by 2700 multiplied by 32100 times dt. And so, therefore, you can now see that this will come out to be the right hand side, this parameter comes out to be how much? This is equal to 1.736 into 10 to the power minus 3, that is the value. So, the encircled entity 1600 multiplied by 940 divided by this is equal to 1.736 into 10 to the power minus 3. So, therefore, you can perform this integration very easily, and then you can say that 1.736 into Tm, where Tm is the complete melting time, which is equal to Tf minus Ti, okay, into 10 to the power minus 3, and that is going to be is equal to nothing but 0.025. Okay? And then you can find out that Tm will come out to be something like 14.45 seconds. So, you can assume that in a steel bath, if you project aluminum sphere, it is almost going to melt instantaneously. Okay? So, you can understand that, so you can take, if you increase the size, for example, okay, because this side, it is a constant, dr dt is constant. So, therefore, because right hand side is constant, so therefore, if you increase the size, double the size, in that case this is going to be also double, because the right hand side is independent of radius itself. Okay? We have made a lot of simplifications, but nonetheless, okay, actually one of the simplification here is, I must mention, and which is discussed, particularly in transport phenomena courses, that during this is an unsteady process, during the melting period, the radius of the sphere actually decreases. So, a constant value of heat transfer coefficient may not be applicable in this particular case, because the radius itself, what is the Nusselt's number diameter. So, we have said that H is equal to heat transfer coefficient is equal to 2 multiplied by diameter of the sphere, and then this is equal to Km. But this itself is a function of t, because the sphere is shrinking as a function of time. So, essentially, truly speaking, heat transfer coefficient is a function of time, and in that case what happens is that the right hand side will become a function of time, and therefore, you will have to, or function of radius, and then you will have to do a little bit more complex integration than what I have been told in this particular case. So, this is a major assumption that you have made, that treat heat transfer coefficient to be constant and is independent of the radius of the sphere, okay? And for calculation of heat transfer coefficient, apply the initial radius, which is an assumption which we have made in this particular case. I want to now illustrate from conduction. So, conduction, convection, radiation, these principles are important, and you must have them at your fingertips, particularly the rate laws, the governing equations, etc., to the extent possible, so that you should be able to calculate or solve various numerical problems. I want to now talk about a little bit about unsteady state heat conduction, a problem I will propose, unsteady state heat conduction. And solve one problem, okay, just to demonstrate to you the principle. And you must understand that this kind of an equation, for example, what I am discussing in the context of heat transfer, will be exactly applicable to mass transfer cases also, that we will see later on, okay, when we talk about the diffusion phenomena and so on and so forth. So, let us pose a problem, unsteady state equation, we all know, and we will solve always one dimensional problem, okay. We will always solve constant property problem, because otherwise we really cannot solve these problems numerically, analytically. So, these are our unsteady one dimensional heat conduction problems. So, let us one dimensional, let us say this is a Cartesian coordinate problem. So, there is a slab geometry here. So, y is equal to 0, So, this is y is equal to L minus L, this is y is equal to plus L. Thickness, the x and the z directions are infinite. There is no heat transfer along x and z directions. And initially, I say that the slab, again I put it in steel because the properties of steel are known to us. We remember them offhand. So, let us say that this is a slab of thickness 2L having an initially uniform temperature field. How we express that? We say at time t is equal to 0, the initial for all values of y. So, y greater than minus L, less than plus L, and temperature is equal to T I, which is equal to 100 degrees centigrade, let us suppose. That is what we express, and right, and then we have say the boundary conditions t greater than 0 for y is equal to plus minus L, we have T is equal to T surface is equal to 1000 degrees centigrade. 1000 degrees centigrade. We want to find out that at a time t that I will prescribe, maybe 1 hour, 2 hour, 10 hours or so, at a given time t, what is the center temperature, center point temperature. That is the task. We are given that the thermal conductivity of the material is 40, and then we are given that specific heat of the material is 680. When I do not write the units, I mean that they are all in SI units. Okay? And now, we can say that, and the density of steel is also symmetrical. So, the governing equation, one dimensional unsteady state heat conduction, okay? And in Cartesian coordinate system, this is x, y, z system. So, we can say that the governing equation is rho Cp, and this is equal to K that is the governing equation subject to the boundary conditions. It is good to work, unsteady state heat conduction. Many of you know that with a non-dimensional version, and that non-dimensional version basically is this is the non-dimensional version of the equation. And then I can say that look, where theta is defined as Ts minus T, and I have used that notation, okay, Ts minus Ti, where eta is equal to y by L, and tau, the dimensionless time, is equal to alpha T by L square. If you use all these parameters, and then you can very easily derive this equation. This is given in the textbook, and this form must be known to you. Same is unsteady state mass transfer with diffusion coefficient here, we will get a similar kind of a relationship. Whatever I am saying with regard to an unsteady state one dimensional heat conduction is equally applicable to unsteady state one dimensional diffusion phenomena in solid. Verbatim application is possible, and therefore, I can say that look, now the modified with respect to theta, the boundary condition will be at tau is equal to 0, okay, for eta is equal to minus 1 plus 1, and then I will say theta is equal to T s minus T I, which is equal to 1. And then I can say that for this tau greater than 0. So, if t is greater than 0, tau is greater than 0, then we have eta is equal to plus minus 1, and then we will say theta is equal to 0. That is what it is. Then T s minus T s divided by T s minus T s is 0, and that is reflected. So, these are translated boundary conditions, and for this we have the solution, and for that we know that for a Cartesian geometry the solution comes out in a infinite series form. Okay? And in the case of cylindrical and spherical coordinate system, we have Heisler chart, because cylindrical coordinate system, if you try to solve this equation, you do not get an infinite series, you get Bessel functions, for example. Okay? So, those are given in terms of, most of you may have used those Heisler chart in order to solve the problem, but in this case we will not use Heisler chart, we will use an infinite series solution, and here the infinite series solution is given in terms of theta as a function of eta, and tau is given in terms of the infinite series solution, and that infinite series solution is 2 summation 0 to infinity, and where it is n is equal to this, and therefore, this comes out to be minus 1 raised to the power n, and then we have n plus half pi. Product solution technique is used, that is why there are two kinds of functions here, exponential minus pi square divided by 4 into, sorry, this is exponential, one term I have missed, minus n plus half squared pi square into tau, okay, and the cosine of n plus half into pi. Let us say that we want to find out the solution to this equation at tau, which is known as the Fourier number, is equal to 0.4. You can understand now what I said, alpha t by L square is equal to tau. So, therefore, the tau, the t we are talking about is 0.4 L square by alpha. So, that is the time we are talking about. Instead of giving you a dimensional time at a given time t, I am giving you the non-dimensional time, and that non-dimensional time is 0.4. Why I am giving? You must remember that when non-dimensional time is going to be greater than 0.2, you will see that this term will have almost 0 value, and therefore, the contribution from the second term will not come, or the third term will not come into the picture, because there is an infinite series. So, it is only the first term which will remain meaningful, okay, at large Fourier number. So, if that is the case, then we can say theta, okay, and we want to have large time. So, it is 0.4, and therefore, our expression is going to be 4 by pi. Only the first term after expansion is, okay. So, 2 and then 2 multiplied by 2, because n is equal to 0, this is equal to 1, and then we have 4 divided by pi, that is the first term, and then it is going to be exponential, okay, multiplied by minus pi square, tau is equal to 0.4, and divided by, you have, because the cosine function vanishes, okay, it assumes a value of 0 the moment theta is equal to 0, because we are concerned about the center temperature, and therefore, we can say that this is equal to, we will write not eta, because this is equal to 0. Eta is equal to 0. So, we are trying to determine the value of theta, and from theta, because theta is defined as here, we will calculate the center point temperature, no problem, because it is the moment we calculate the value of theta, because Ts and Ti are known to us, the center temperature can be calculated. So, theta at eta is equal to 0 is actually Ts minus Tc divided by Ts minus Ti. So, the center point temperature can be calculated. So, now we can find out that what is the value of this particular parameter, okay, and this parameter comes out to be 475. You can just use a calculator and the value can be known to you. So, therefore, now we can say that theta at 0, 0.4, okay, which is equal to now Ts minus Tc divided by Ts minus Ti, and that is going to be equal to 0.475. So, therefore, now we can calculate the center point temperature very easily, and that center point temperature comes out to be Tc. By solving this equation, okay, we will see that Tc comes out to be 573.5, and that is degree centigrade. So, therefore, this is an application of the unsteady state heat conduction principles, okay, and for slab geometry we have solved, and as I said that you should be able to solve the problems instead of giving the solution to you. This solution, such solutions are typically given, and then it is asked that, you know, what is the center point temperature, what is the heat flux, and so on and so forth. So, one thing we have to, we must remember that the moment we set that the Fourier number or the dimensionless time is greater than 0.2, we can forget about the second, third, fourth and fifth term in the infinite series expressions and do our calculations based on the first term. This is a very important deductions. So, when we have slab geometry, of course, we have chart, Heisler chart, but we can start with this equation also, do not get scared, okay? Understand the problem, set the boundary conditions correctly and so on and so forth. But in the case of cylindrical and spherical geometries, as I have indicated, that you will be provided more, you know, the Heisler chart rather than the governing solution of the governing equations, and you should be able to read the Heisler chart properly, because I cannot write, you know, draw the Heisler chart here. So, I think the same principle applies there also, okay? You find out non-dimensionalization is an important exercise. You must, this must be in your fingertip, that how to convert the equation into a non-dimensional form and translate the boundary conditions which I have shown here into the corresponding non-dimensional form, and then the reading of the Heisler chart is going to be a piece of cake for you. So, we will end up our lecture today here, and I think next lecture I will talk about you know, steady state and unsteady state diffusion, and then we will solve some interesting problem of practical applicability.